Hi everyone, this is Hanson here. I'm ready to share my Module 5 test review session with you on buffers, titrations, and the additional aspects of Equilibria, specifically the common ion effect and KSP, the solubility product constant. I'm unable to schedule a live review session this week with just a crazy week of meetings, so I decided to record and send you the video. So with no further ado, let's begin. I'm going to turn my webcam off so we can focus on the screen. Let me do that now.
Bronstead Lowry proton transfer. The HNH3 is going to combine to form the ammonium, the conjugate ion of ammonia, and the spectator ion nitrate, NO3 negative. A proton has been transferred. We said HNO3 is a strong acid. Its conjugate base is nitrate, NO3 negative. What we also know is that the negative ion of a strong acid is called a spectator ion. It will not undergo hydrolysis to form or affect the pH of a solution. The nitrate has no effect on pH since it is an anion of a strong acid. These two are conjugate pairs where the HNO3 is the acid and the strong acid 100% dissociates to create a spectator ion of nitrate. Now let's consider the ammonia, which we said was a weak base. So therefore, its conjugate acid is ammonium, NH4+. Here is the base and here is its conjugate acid. That's Bronstead-Lowry review. We were given 0.23 moles of HNO3. See how I'm just tallying that under the HNO3, and we put that into a liter of solution, which now tells me it's 0.23 molar. And in the ammonia, we have a 1 molar solution. Look at the stoichiometry of our reaction. We have a 1-to-1 acid-base mole ratio. If we have 0.23 moles of HNO3 and 1 mole of ammonia, we can clearly see the smaller number is going to be the limiting reagent, and it will consume all of the nitrate of the HNO3. There's none left at equilibrium. Along the way, it also consumed 0.23 moles from the 1 mole of ammonia. When I look at HNO3 plus NH3, the chemistry there is simply showing us that we were going to have excess amounts of ammonia, NH3. 1 minus 0.23 is 0.77 moles of excess amounts of the ammonia. We also know that 0.23 moles of ammonium would be made and 0.23 moles of the nitrate will be made. So what's present when this reaction has reached equilibrium? Well, we can see that we have 0.77 moles of ammonia. That's the base present in this solution. The strong acid has been consumed. The HNO3 is not present, but the conjugate acid of ammonium is present. There's our NH4+. And what about this other? The other means not an acid, not a base, but a spectator ion. And in this case, we said the anion of nitrate would be that spectator. The NO3 negative does not behave as an acid nor a base because its parent is strong. Therefore, it's considered an quote, other category. So that was easy enough. Just using stoichiometry, we were able to determine what was present in solution as the major species. The base of ammonia, the acid of ammonium, and this other species called nitrate were the species present at the conclusion of the equilibrium reaction. What if we were to take HNO3 and combine it with ammonia, knowing that we have a proton transfer, and we also include ammonium chloride as well. So this was taking off Alex, where we were given 0.07 moles of the nitric acid, and we were given 0.7 moles per liter, so 0.7 moles of ammonia, and we were given 0.7 moles of ammonium chloride, all in that liter of solution. What's present as the major species in equilibrium? Well, let's first conclude that we see that the strong acid is indeed the limiting reagent. And along the way, I see that I have 0.63 moles of the ammonia left at equilibrium. I have 0.07 moles of ammonium present at equilibrium. And I have 0.07 moles of nitrate at equilibrium. Since nitrate, NO3 negative, is the anion of a strong base, it will not undergo hydrolysis. So this is considered not an acid, not a base. It's the other, quote, other category. Here I can see the major species is the base. I can see the major species is the acid here, ammonium, and I have nitrate. And what about this salt that we added? Ammonium, we said, was already present, but we're going to add even more ammonium from the ammonium chloride we added. So when we're finished, we have 0.77 moles of ammonium, and we still have this chloride, right? NH4 plus and Cl negative is a salt. We said we had 0.7 moles of ammonium and 0.7 moles of chloride when that salt dissociates. So not only do we have nitrate, NO3 negative, as another, we also have the chloride. So there's two answers in this category when you looked at your Alex. The nitrate and the chloride are both anions whose parents are strong and therefore do not affect pH upon hydrolysis. The base that was present is ammonia, and the acid that is present is its conjugate called ammonium. This one was review from your Alex assignment. How did you do? Pause the video if you need a moment to process, and let's look at another when ready. Here we have a titration problem. It reads, an analytical chemist is titrating a 119.1 ml of 0.53 molar benzoic acid. I'm going to just make a notation for any acid as HA. This is my way of writing benzoic acid. And I'm going to titrate that with sodium hydroxide. Now that one they give me a formula for, so I'll write it out. NaOH, sodium hydroxide. Let me tabulate what we were given underneath. It says we're titrating 119.1 mils of the acid. That is 0.53 molar concentration. See how I like to tabulate what I'm given right underneath the ingredient in my balanced equation. The concentration of the base is also given as 0.96 molar solution. All right, over here to the side, the pKa of benzoic acid is 4.20. We'd like to know the pH of the solution after the chemist has added 76.52 mils of the sodium hydroxide. And we're always told in the titration problems in Alex to include 2 decimals in our final answer. I can go ahead and finish what we're producing over here. An acid and a base come together and form a salt and a water. So we would have just to kind of figure out what these words are. This is sodium hydroxide is our base. An acid plus a base. Here is the water. And then here would be what we call sodium benzoate, the salt. Now, knowing that the sodium is a spectator ion, it is certainly fine to eliminate that spectator. I know it's a spectator because it's the cation of a strong base. So you could choose to simply write OH negative, and over here you could choose to just write A negative and eliminate the spectator. What that helps me see is that I have conjugate pairs. I have HA and its conjugate base A negative. These are conjugate pairs. This is its acid and this is its conjugate base. I'm emphasizing that because I notice right away that this is a buffer solution, right? I have the ingredients of a buffer. So it's something I just recognize. I also recognize that sodium hydroxide is strong and benzoic acid is weak. So if the HA and A negative is present after the titration, I know to use Henderson-Hasselback to find pH. If the strong base is present, it will determine the pH directly, and therefore no Henderson-Hasselback is required. So it's very critical to decide what's the limiting reagent, what's the excess reagent. After this reaction is completed, what is left in solution? Do I have conjugate pairs? If so, Henderson-Hasselback. Or is the excess reagent the strong base, and therefore anytime I have strong excess reagent, it's a straightforward pH calculation? Let's take a look and see how this one works out. For the acid, I'm going to multiply molarity times milliliter, and I like to get something called a millimole so that my numbers are more friendly to use. When I multiply 119.1 mils times 0.53 molar, my calculator reads 63.123 millimoles of the acid. When I calculate 76.52 times 0.96, I find the millimoles of the base. When I hit that on my calculator, it read 73.4592 millimoles. Milliliter times molarity, millimoles. Now investigate. Which one is the excess? Which one is the limiting reagent? Well, here I can see the smaller number clearly is coming from the acid. So when the reaction is finished, there is no acid present. And we would also consume 63.123 millimoles of the original value, 73.4592 of the base. How much base is left over? When I subtract those two, I found a number that read 10. No, it didn't. Oh yeah, I'm going to re-hit just to be sure. Patience, please. 73, I don't want to make a mistake, 73.4592 minus 63.123. Did you hit with me? My screen reads 10.3362 millimoles of the hydroxide ion as the excess reagent. Yes, that's a match. Okay, so because the strong base is in excess amounts, we use it to directly calculate the pH at this point in the titration. Here's what we know. pH is equal to the negative log of the concentration of the hydrogen ion. We also know this formula. pOH is equal to the negative log of the hydroxide ion concentration. And we know that relationship between those two numbers is always 14. Remember that these brackets stand for molarity, not moles, not millimoles. We've got to change the millimoles back to molarity. I'm just writing that out so you write it in your notes as well. We had a 10.3362 millimoles of hydroxide in a new combined volume. And this, if I'm going to make a mistake, seems to be in this spot right here. Oops, I wrote if. The new combined volume during the titration. This is so critical to remember. I don't have just 76.52 mils of the base anymore. I have 75.6, moment of dyslexia, sorry, 76.52 plus the 119.1 mil of the combined volume. See what I'm doing? Millimole over combined volume in a milliliter will find for me the new molarity. Take your calculator, 10.3362 divided by the sum of the acid plus the base volume, and you will find the molarity of the hydroxide ion. And my screen is reading 0.05284. So I can find the pOH by taking negative log of 0.05284. And when I do that, I say 14 minus that, and I'll have our pH directly. So there's our pathway yet to take. Let me give you a minute to pause. Pause the video, finish this problem, and then turn it back on to see if we get a common answer. All right, welcome back. I'm showing my calculator reading 12.72 pH units. To remind yourself how you got there, we took the millimoles, the excess reagent was a strong base, and we divided by the new combined volume. So critical to combine the volumes for molarity. When you took negative log of 0.05284, your screen read 1.277, but remember that was the pOH. 14 minus that answer got me 12.722 or 23. All right, so here's the critical part of this example problem. We had to first find which one was the excess reagent. If I had a conjugate pair in presence at the end, I would use Henderson-Hasselback. Or if, as in this case, we had a strong base or a strong acid present, we use that molarity directly to solve for the pH. Good work. Okay, take a break as needed. Pause, come back. That's the beauty of a video. Our next test prep question. We have an analytical chemist titrating 96.6 mils of a 0.56 ammonia. All right, so let me just pause. I'm going to write down some ingredients. I see the base we are using is ammonia. It's given to me as 96.6 mLs, and its concentration of 0.56 molar. We're reacting that with a strong acid. This is chloric acid, HClO3. There, make that neat. So we have a weak base versus strong acid titration. This concentration is 0.087 molar. Good thing I can erase. Just to finish the chemistry, we would have a proton transfer, ammonium, and the chlorate anion would form. So the weak base forms its conjugate acid, ammonium, and the strong acid forms its conjugate base, chlorate. Recall that this chlorate is a spectator ion. The anion from a strong acid will not affect the pH. But I do have the key components of a buffered system, a base, a weak base with its conjugate acid. So we know that these two are ingredients for buffers. But it all depends upon what's left at the end of this titration. Remind yourself, if you have the conjugate pairs, I'll just write that. How about if I write, if the weak base are present, then I know that that means to use the Henderson-Hasselback equation. pH is equal to pKa plus the log of the ratio of base over acid. That's my Henderson-Hasselback. However, if strong acid is present, I'm talking about the excess reagent, then you calculate pH directly. No Henderson-Hasselback, just pH equal negative log of the molarity of H+. So that's what we have to decide. Where are we at in this titration? And of course, this is finding one that has the excess reagent. So let's continue reading. It tells me the pKb of ammonia is 4.74. Calculate the pH of the base solution after we add 8.1 mil of the acid. So that's that last ingredient there, 8.1 mil. I'm going to take molarity times milliliter and get a millimole and decide what's the limiting reagent and what's the excess reagent in this titration. So just think of this as an ice chart, right? Initially, we have 96.6 times 0.56, just hitting that on my calculator, and it reads 54.096 millimoles. Here I have 8.1 times 0.087, and that reads a very small number, 0.7047. So what's the limiting reagent and what's the excess reagent in this calculation? Well, it's very clear to see. The smallest number is going to be 0.7047. So the strong acid has been completely consumed. Along the way, it also consumed 0.7047 millimoles of ammonia, and it formed 0.7047 millimoles of the conjugate acid, ammonium. And remember, it also formed chlorate, but since chlorate is simply a spectator, I'm not even going to consider that in part of my problem. The anion of a strong acid will not affect pH, so just toss out considering it. But what do we have left in solution? Whoops, sorry. Sorry about that. Let me just subtract what we had, 54.096 minus 8.1 times 0.087, so minus 0.7047. and that's 53.3913 millimoles. And the conjugate acid is present in that same amount. So since we have a conjugate pair present in solution after the titration, we're going to use this formula called the Henderson-Hasselback. pH will be equal to pKa plus the log of the ratio of the base over its conjugate acid, ammonium. Now remember, the pKb was given, and we need the pKa for this formula. Easy enough. 14 minus the pKb will be my pKa, right? Their sum will always be 14. So that gives me 9.26 as the pKa of the system. The concentration of ammonia, 53.3913. Let me come over here. Give myself some room. Plus the log of the ratio of the base, 53.3913 millimoles, over the conjugate acid of 0.7047 millimoles. I'm going to take 53.3913 and divide it by 0.7047 and simplify. And then I'll take the log of that answer and add that to 9.26. And at this point in our titration, the pH is reading 11.14. My screen reads 11.1394, and I'll just round to 2 sig figs. What do you think? I'm going to diverge for a moment. A common question I get is, why is it okay to use millimoles over millimoles in this equation instead of molarity? And here's the answer. If I had 53.3913 millimoles of the base, and I have 0.7047 millimoles of the conjugate acid. When I divide that ratio, we saw that we got a number 75.76. If I include the combined volume to turn this into molarity, I'm dividing by the same number in each of these ratios. So I wanted to write volume, and I just wanted to share how that does not affect the final answer. We had 8.1 mil combining with 96.6 mils. That's a total of 104.7 mils. But if I simply am dividing both of these numbers, they cancel, don't they? See what this does? If you solve for this, and I can hit this with you, no worries. I'll take 53.3913 and divide it by 104.7. I get a number that says 0.5099 molar units. Let me do that. 0.7047 divided by 104.7. And here the molarity comes out to be 0.00673 molar units. Divide those two and you'll find that you have the same overall ratio. So I'm finding this number again. The moral of the story is, when you use Henderson-Hasselback, it is okay to leave them in millimole ratio. That the Henderson-Hasselback says the conjugate base over the acid, that this bracket can be molarity, and that's what it stands for, but since it's a ratio, it can also be left in a millimole and still be fine when you calculate the overall ratio. When I use pH, I cannot leave this in millimole. The pH must be molarity. I must use the combined volume to turn that into molarity, because it's not a ratio in that formula, is it? And because it's not a ratio, I must have a molar unit. Okay, enough pontificating on the math, but I did want to make a side note. Henderson-Hasselback, since it's a ratio, I can leave them in millimoles. But if the strong acid or the strong base is in excess amounts, it must be in molar units, moles over combined volume. Take a break, pause, take a deep breath, come back when ready. Let's take a look at a next example. A chemist titrates 50 mils of a 0.3397 molar solution. The solution is potassium hydroxide, KOH. Let me tabulate what we have under it. We have 50 mils, 0.3397 molar units. It's titrated with HBr. We have 0.3280 molar units. Calculate the pH at the equivalence point. Friends, what do you notice about this problem that makes this the easiest problem ever? We are titrating a strong base with a strong acid. You have those memorized, don't you? That HBr is strong as well as KOH. When a strong acid and a strong base is titrated, the equivalence point is always 7.00. There's no math. This is the easiest problem ever because there's no math necessary. The equivalence point is neutral. And the key is that's only true if strong versus strong is titrated to the equivalence point, where the number of moles of base equal the number of moles of acid. The very definition of an equivalence point is mole of acid equal mole of base. We know that we made salt water on this side, but remember the cation from a strong base, no hydrolysis, no effect on pH. The anion from a strong acid, no effect on pH because no hydrolysis. This KBr has no effect on pH. So you're just looking at a neutral solution of salt water. 7.00, no math. I like those. I'm going to keep working some titration problems as those seems to be the biggest stumbling block at this point. I do have later in the video some KSP problems, so stick with me or fast forward if you'd like to go through some of those. A chemist titrates 110 mils of 0.4406 molar aniline. Now notice the nitrogen. This to me says this is an ammonia derivative. I know it's going to be a base. And a base will react with an acid. So I'm going to write aniline as B, just because it's an easier way to keep track. I know the base is C6H5NH2. But instead of writing that all the time for my homework here, I'm just going to write it as B for base. And it's going to react with HCl, forming conjugate pairs, BH positive and Cl negative. The anion of a strong acid is a spectator ion. No effect on pH. I do have conjugate pairs that this I know meets the criteria of a buffered system. B positive or BH positive is the conjugate acid of the base, and that these two are conjugates, but it's not a buffered system because a strong acid cannot form a buffer. Let's tabulate what we have. We said we were given 110 mils of a 0.4406 molar solution of the base, and we titrate that with 0.8210 molar of the acid. We don't know how much that is, but we can determine it because we're at the equivalence point. Now notice, this is a weak base, strong acid. So when it says at the equivalence point, the answer is not easy, right? It's not 7.00. That's only true for strong versus strong. Here we have a weak base, strong acid. But at the equivalence point, we need to make a note that this turns into a hydrolysis problem. And let's model why. At the equivalence point, the only thing present in solution will be the conjugate acid, the BH+. So I'm going to hit on the calculator here. I'm going to find 110 times 0.4406, and this gives me 48.466 millimoles of the base. The very definition of equivalence point says moles of base equal moles of acid. So I know that there's 48.466 millimoles of the HCl as well. That's the definition of equivalence point. Moles acid equal moles base. Now I can work back to find the volume it took to deliver 48.466 millimoles. Remember that moles per liter equal molarity. And I've just been using millimole over milliliter is molarity. So that's fine. The units agree. A round little buddy, if you like that kind of system, I often use this with beginning students. Just kind of an algebraic representation of those units. Here I'm given 0.8210 molar, and the number of millimoles was 48.466. We'd like to know volume. So you can see that there's one set over the other. The millimole, 48.466, divided by the 0.8210 molar units is going to give me the volume in milliliters. .466 divided by 0.8210. And my screen reads 59.0329. That's plenty of decimals. Why don't I say 033? And that's the volume it took to deliver that. Alrighty. So we have an equivalence point, meaning that as I think about the initial, which would have 0, remember spectators just fall out, the change is going to be 48.466, so that none of these are left over, right? Those are consumed, very definition of equivalence point, but what's made is 48.466 millimoles of the BH positive in a new combined volume of 110 mils plus the 59.0329 mils. This was the original base, and this was the acid in the new combined volume. And what is the molarity of the BH positive in solution? 110 plus that volume is the new combined volume of 169.032 mils. Take your 48.466 and divide by that value, and the molarity I'm finding is 0.287. So we are at the equivalence point, meaning this is the only species left in solution that will affect pH. What is the pH when we have that concentration of BH positive? It turns into a hydrolysis problem. We've learned that a conjugate acid will hydrolysize, which just means reacts with water. The BH positive, when acting with water, we have a proton transfer. The conjugate base and hydronium form. If this is the acid, this is its conjugate base. Therefore, water is acting as the base, forming its conjugate acid. That's just Bronstead-Lowry proton transfer. And we can see that the concentration of the BH positive we've worked to find as 0.287 molar units. Let's let the base represent by X and the hydronium also be X. We need a Ka for this problem since we made hydronium. I got to scroll up to find what we were given. 4.87 is the pKb. Let me write that down. That means the Ka or pKa, I can do that next. I'm going to flip pKb into pKa by taking 14 minus 4.87, and that's 9.13. 10 raised to the negative 9.13 gives me the Ka. 10 raised to the negative 9.13, and my screen reads 7.413 times 10 to the negative 10. This is the Ka we need to solve for X. (7.413) times 10 to the negative 10 is equal to X squared over 0.287 molar units. That's our products over reactants, just a straight Ka problem. I'm going to cross multiply, take the square root, and solve for X. So X is equal to the square root of 7.413 times 10 to the negative 10 times 0.287. That's what I'm doing on my calculator to pull out X. And remember, X was hydronium in molarity units. My screen is reading 1.4579 times 10 to the negative 5th molar units for the value of X. To convert that into pH, we know to take negative log of that concentration. And what'd you find? Please remember to pause the video at any time and just practice these calculations. You need to not only be proficient, but know what to do with relative speed to be able to finish your quiz or your test in time. My screen is reading 4.84 pH units. Is yours as well? My gosh, we've been doing such good work with titrations. I've shown you strong versus strong at the equivalence point. I've shown you weak versus strong in any variety of excess or limiting reagents. So these titrations allow us to practice a lot of buffers and just concepts of limiting and excess reagents and applications of equilibrium problems. Let's turn the table a little bit and start a new topic, looking at some KSP, some common ion, and molar solubility example problems. I do find that these, in terms of ease of problem, these are much simpler than titration problems. I think you'll agree. Here we have an example I pulled from the quiz. It says we have a solubility of silver chloride. So AgCl as a solid is going to dissociate a little bit into its aqueous ions, silver and chloride. So that's our equilibrium when we talk about solubility product constant. The solubility of AgCl is measured to be 0.0019 grams per liter. Calculate the KSP for silver chloride, the solubility product constant for silver chloride. Well, I know that the expression for KSP is going to be equal to the molarity of the silver ion times the molarity of the chloride ion. And remember, pure solids drop out of our equilibrium expression. So the left side is never included in these KSP problems. Key component here, though, recall, is that brackets are molarity, which is moles per liter, not grams per liter. So you need to convert gram per liter into moles per liter. That's really the only trick to this particular problem, is making sure you had your units set up correctly. If I had 0.0019 grams of AgCl and wanted to convert that into a mole, I would divide by its molar mass. Let's see, I know silver from the periodic table, 107.8, and I know chlorine from the periodic table, I'll say is 35.5. I'm going to add those. 144.3 grams as the molar mass of AgCl. So all I'm doing is a little mole map problem. Gen Chem 1 review. 0.0019 divided by 143.3. And my screen reads 1.3, I'm just going to round a little bit, 1.33 times 10 to the -5th moles. So just thinking about what we just did, I converted gram per liter into moles per liter with just a little mole map problem. 0.0019 grams is equivalent to saying 1.33 times 10 to the -5th moles. And now that I can see we have an equal distribution of silver ion and chloride ion, this will dissociate into equal amounts. Those simply become the same number over here. So as this dissociates equal quantity, now we have the number we need to calculate. So 1.33 times 10 to the -5th moles per liter is the concentration of silver ion, as well as the chloride ion, since the salt dissociates into a 1-to-1 molar ratio. So while that's on my screen there on the calculator, 1.33 times 10 to the -5th, I'm just going to square it. And when I do that, I find that KSP is 1.76. I'll round a little. No units on a K constant. Easy peasy. Okay, let's challenge ourselves a little bit more. Let's look at an example where we're given the solubility in grams per liter. Calculate the solubility in grams per liter of lead 2 carbonate, PbCO3, in pure water and in a solution of lead 2 nitrate. So we need two different answers. We have two different questions here. First, let's get an idea that when this dissociates, I'm going to get a 1-to-1 ratio of its aqueous ions. So in pure water, we have no common ion. It's giving me 0.00, whoops, we want to know, oh, we got the KSP. Okay, I'm sorry, I have to just kind of read that. The KSP is given to us, and we know that that's going to be equal to the concentration of lead in molar units times the concentration of carbonate in molar units. The KSP is provided as 7.40 times 10 to the negative 14. Why don't we just let the value of X represent the ion lead? And since it's a 1-to-1 dissociation, we'll also let X represent carbonate. So this just simply becomes X squared. Taking the square root of 7.4 times 10 to the negative 14th. My screen reads 2.72 times 10 to the negative 7th is the value of X. Remember that X is the molar solubility. Brackets stand for molarity, moles per liter. So we were asked to solve for that in grams per liter, right? Here's your little mole map, if you recall. Grams over molar mass is a mole. So we were given 2.72 times 10 to the negative 7 moles. We'd like to know grams. Pb has a molar mass of 7.2. Carbon is 12. Oxygen is 16, but there's 3 of those. So let me just find the molar mass of lead 2 carbonate. I'm summing those and finding 2.2 grams. Mole times molar mass will convert to a gram. So 2.72 times 10 to the negative 7 moles times our molar mass of 267.2 grams per mole. And my screen is reading 7.27 times 10 to the negative 5th grams per liter. There is the gram per liter solubility of lead carbonate in pure water. Let's suppose instead of dissolving in pure water, let's put it into a solution that contains a common ion. And it's giving us 0.009 molar of lead 2 nitrate. What common ion does lead carbonate and lead nitrate have in common? Well, clearly you see it's the lead. So instead of saying X and X as we did up there in the pure water, we're adding an additional 0.009 molar. Let me make that neater. We have X from the dissociation and an additional amount of 0.009 molar units of the lead from the common ion lead 2 nitrate. Our KSP of 7.4 times 10 to the negative 14th is going to be equal to 0.009 plus X, the concentration of the lead ion, times the concentration of the carbonate ion as well. And we've learned much practice to say, since this is so small, toss it out, right? It's negligible. So you're going to find essentially the same answer as if you just said 0.009 instead of saying 0.009 plus X. Solve for X. 7.4 times 10 to the negative 14 divided by 0.009. And my screen is reading 8.22 times 10 to the negative 12th molar units. I want to think about just finishing this problem and then applying Le Chatelier. We said this is the molar units, so I can convert that as well, just like we did above, by using the molar mass of 267. So that was just me adding PbCO3's molar mass. And that answer came out to be, I'll just round a little bit, 2.2 times 10 to the negative 9 grams per liter. Email. Le Chatelier's principle says, when I add an additional amount of the lead ion, that's our stress, that it wants to alleviate the stress, it wants to eliminate the stress, it wants to reduce the carbonate or the lead ion. So that's going to cause this equilibrium to shift left. By adding more lead, as we did with the common ion effect, you decrease the solubility. Notice that we had a negative 5, whoops, I hit the button. We had a negative 5 ion power here, and down here we had a negative 9. The solubility decreases upon the addition of a common ion. I'm trying to write neatly with my stylus pen. Sometimes it doesn't go well. Oh my goodness, we did great work here. We worked a KSP problem in pure water. We noticed that when we added a common ion, the solubility decreased, and we recalculated to find the new concentration. We did so in both molarity and in grams per liter. So it's very easy to convert from moles to grams or vice versa, remembering that it's molar mass that converts one to the other. How are you doing? Take breaks as you need it. A lot to get ready for our test. I'm going to keep going with some example test questions. Some of them are not mathematical. I just wanted to kind of keep going on conceptual ideas of the common ion effect. Here's an example test question that asked me to consider the following. I have an aqueous solution of ammonia, and I'm going to add a strong base to it. So remember, this is a strong base. NaOH, strong base, and this is a weak base, ammonia. When ammonia is in a water solution, it sets up conjugate pairs of ammonium and hydroxide. So this is just Bronstead-Lowry proton transfer. Ammonia is the base. It forms its conjugate acid called ammonium. Water, therefore, is acting as the acid, forming its conjugate base, hydroxide. If we add NaOH, what is the common ion in NaOH to this equilibrium expression? Well, clearly you see it's hydroxide, right? NaOH contains hydroxide ion, so the stress is really saying I'm increasing hydroxide ion. When I add strong base into this equilibrium, this is a stress. The initial stress is increasing the base. That we know is going to force the equilibrium to shift left to alleviate that stress. And as it does so, what happens? Well, as it shifts left, the ammonium gets consumed and it makes more ammonia. What happens to the pH when this occurs? Well, adding strong base increases the hydroxide ion, makes the solution more basic. So what happens to the pH as it becomes more basic? The pH is going to increase further away from 7, which is the point of neutral. So this is a true statement. The pH of the solution should increase. It's becoming more basic by adding a strong base into the solution. Makes sense? The concentration of ammonium, we decided, decreased, and the concentration of ammonia actually increased, all because we applied Le Chatelier's principle with a common ion effect. So all three of these statements ended up to be true. So when you're looking at these types of problems on your test or quiz, apply Le Chatelier's principle. It's really just an application of a common ion effect in disturbing equilibrium. Shall we try another thought question? When mixed in appropriate amounts, which of the following mixtures can produce an effective buffer? Except, so we're looking for the exception, which means it cannot produce. Well, I know a buffer, in order to produce a buffered system, we need a weak acid and its conjugate base, or we need a weak base in its conjugate acid. Those are the two criteria. So let's kind of pick these apart one by one and see if it meets the criteria of a buffered solution. We know sodium is a spectator ion. So here we have HPO4 minus 2 with PO4 minus 3. Are those conjugate pairs? Conjugates differ by just one hydrogen ion. So yes, these are conjugates. This is the weak acid and this is its conjugate base. So yes, this is a buffer. What about letter B? At first, this is a little tempting to say no, because I don't see these two have anything in common, sodium dihydrogen phosphate and HCl. But I'm adding these together. I'm going to just make a note. I'm adding together HCl and NaH2PO4. What comes out? H goes to H2PO4 and Na goes to Cl. That's just the old double replacement reaction, right? The two positive ions exchange places. H plus and Na plus exchange places in this reaction. So what do you have at the end of this are conjugate pairs. We have present in solution H2PO4 and H3PO4. So yes, adding a strong acid to that salt, sodium dihydrogen phosphate, did produce conjugate pairs, So yes, this is going to make a buffer. How about letter C? Well, this one is easy enough. I have HCO3 negative and I have CO3 negative 2. Those are conjugate pairs. Here's an acid and its conjugate base. Sodium is the spectator. What about letter D? Well, what's interesting here is I have the same first name, right? So sodium hydroxide to sodium fluoride. Even if the two positive ions exchange places, you haven't made anything new because the first name is the same. So this is no chemistry. So this will be no, there's no conjugate pairs. All that's present is solution is sodium ion, hydroxide ion, and a fluoride ion. No buffered solution will form. Spectator. So yes, these are conjugate pairs. So the only system here that would not form a buffered solution is letter D. Cool. We're in the home stretch. I'm going to keep working as many examples as you want to stick with me with. Which salt should be the aqueous solubility the most sensitive to pH? Here's a list of salts. Last module, we talked at length of the hydrolysis of salts. I can get rid of the first name because it's identical in all of these compounds. Calcium, strong base. It's called calcium hydroxide. And we know that the cation of a strong base has no effect on pH. Plus, since it's the same in all of those choices, choice A, B, C, D, E, it can't possibly be worth considering. I need something unique. So let's look at the anions. The anion in letter A is chloride. It is the anion of a strong acid, no effect on pH. The anion fluoride is HF, parent acid. This is actually a weak acid, so yes, it will affect the pH through hydrolysis. Just to remind ourselves, fluoride will undergo hydrolysis, forming its conjugate acid and making the solution slightly basic. We'll just keep going. Parent acid here, HNO3, this is strong, no effect. Parent acid here, HBr, this is strong, no effect. I can spell and talk at the same time. And then HI is also one of the strong acids, so therefore no effect. The key here is realizing that fluoride is the only anion of a weak acid parent, therefore it will undergo hydrolysis, and therefore it is sensitive to pH. The old chapter kind of coming out several different ways here with Le Chatelier and common ion, as well as the solubility of salts and hydrolysis. Here is another KSP problem, just trying to pull a variety. I have a compound called magnesium hydroxide. And it, of course, sets up an equilibrium with its aqueous ions. When magnesium hydroxide dissociates, it does so by releasing one ion of magnesium, but two aqueous ions of hydroxide. If the molar solubility of MgOH taken twice is 1.4 times 10 to the negative 4th molar units, calculate the KSP of your solution. Well, I know that it would be equal to the molar concentration of magnesium times the molar concentration of hydroxide, knowing that hydroxide has to be squared because coefficients become the powers with which you raise during your equilibrium expression. So thinking about what we have here, magnesium hydroxide to magnesium ion is a 1-to-1 mole ratio. They're going to be the same number. But since twice the number of hydroxides come out, its molar concentration will be 2 times 1.4 times 10 to the negative 4th. And if you plug that all in, the magnesium ion concentration raised to the first power, because its coefficient is 1, times the molar concentration of hydroxide, which is doubled, and squared to find ASP. Doubled and squared when calculating hydroxide. Go ahead and hit that out, and what did you find? And as I finish hitting, looks like I'll round a little bit. It's close to 1.1 times 10 to the negative 11. No units on a KSP. Now I picked this one simply to remind ourselves when finding concentration, think about stoichiometry and remember to use those coefficients as exponents in your expressions. These are so much easier than titration problems. Oh, I picked this problem, just a plain old buffer solution problem, simply because I saw several people miss it on the test last term, and I know we haven't taken it yet this term, so let me kind of give it a read through. We want to find the pH of a solution prepared by dissolving 0.35 moles of solid dimethylamine hydrochloride, and that's a big word. Just write down this formula. CH3 taken twice, that's the dimethyl, and then NH2Cl is the amine hydrochloride. And I'm just going to put that here, 0.35 moles in a liter. And we put that into a solution that also contains dimethylamine. So just think about conjugate pairs as you form this equation. We're going to have a proton transfer. This right here is the acid. This will be its conjugate base. So CH3 taken twice, NH, and the proton then goes to the water, making H3O plus. Now, how did I do that? Notice the formula has 2 hydrogens, and here it has just 1 hydrogen. These are ammonia derivatives. Nitrogen has 3 bonds and 1 lone pair. All I've done in this particular compound is replaced one of the hydrogens with a methyl, the other with a methyl, so that's why you see CH3 taken twice, and then I see HCl coming off the other end. All right, so that's kind of the structure of this particular compound. So you can think of chloride actually as the spectator ion and have just NH plus like this. Alrighty. So just kind of thinking, whenever you see an ammonia derivative, just remember that it's going to always kind of think about proton transfer on the actual nitrogen. Let me just erase that and get myself back to room. So we have 0.35 moles in a liter of NH2Cl, the acid, and its conjugate base, and this was given to me as 1.10 molar units. What is the pH of our solution? Notice that these are conjugate pairs. That was the key, I think, in problem solving. Sometimes we get so nervous that these formulas look so big, but just notice that you have 2 hydrogens here and 1 hydrogen here. Those are conjugate pairs. Chloride is always the spectator ion. Chloride is always soluble. So you could get rid of the chloride altogether and just put a plus sign here, and that way it's more friendly. What's over on this side is just a dissociated chloride as it is on the left side. It's just a spectator, not influencing the pH because its parent is a strong acid. So just disregard it if that makes it easier. I have conjugate pairs. Anytime I do, I know to use Henderson-Hasselback. I'd like to know pH. So I take the pKa plus the log of the ratio of the base over acid. We're given Kb. Let me just quickly turn that into a pKb. Negative log of that given Kb. My screen is reading 3.2676. I need pKa to do my Henderson-Hasselback. So 14 minus that answer, and that's 10.7324, which is plenty of decimals. My pH of this solution will be found by taking that pKa and adding the log of the ratio of the base, 1.10, over the acid, 0.35. When I notice I have conjugate pairs in solution, pH is tackled by taking pH equal pKa plus the log of the ratio of the molarity of base over acid. Solve for that. And I'm finding on my screen 11.2297. So somewhere around 11.23 pH units. Again, I don't think this is a tough problem once you understand it's just nothing more than 2 conjugate pairs, but sometimes the big names and sometimes, the big formulas kind of scare us a little bit. But focus on the nitrogen, letting you know that we have conjugate pairs between an NH2 plus and the NH. And that becomes a straightforward calculation using Henderson-Hasselback. All right, awesome. What else do I have? I'm, again, just trying to show many examples. If you're still with me, terrific. I hope you've taken breaks. I'm just pulling sample problems off of tests, quizzes that have been commonly missed in the past. What is the pH of a buffer? That's a good word to let us know Henderson-Hasselback is going to be involved. Sodium will be a spectator. So I'm looking at H2, and I can put the sodium there, H2PO4. And I'm seeing that I'm going to put in also some Na2HPO4. So I know that these meet the criteria of a buffered solution because I have a conjugate acid and base pair. So H2PO4 negative, and its conjugate base of HPO4 negative 2. So that's what I see when I look at that first sentence. I see, all right, I have a buffered system. I'm given 12 grams of sodium dihydrogen phosphate, and I'm given 8 grams of sodium hydrogen phosphate. And I'm going to put that into 0.5 liters. Let me do some mole calculations here. This says this is 120 grams per mole, and this is 142 grams per mole, respectively. So before I can do any pH calculations, I need to get grams into moles and then moles into molarity. Eight divided by 142. And just remember, the one with more hydrogen is always the acid, and here is its conjugate base. Now, I know that I'm going to use the Henderson-Hasselback equation because it talks about buffers. Plus the log of the ratio of your base over acid. And I did a moment ago, well gosh, probably an hour ago by now, talk about you can do millimoles over millimoles, or you can do a ratio of molarity over molarity. Is that it doesn't matter. This 0.50 liter, I don't really need to even consider it because my ratio will come out the same if I use it or not. So to emphasize that, the ratio of millimoles, 0.1, whoops, I need the base, 0.0563 over 0.1, or 0.1 over 0.5. .0563 divided by 0.2 liters, divided by 0.5 liters, back up Linda, there we go, is 0.1126 molar. I'm emphasizing that you're going to get the same number regardless if you divide by the liters or not. So it's really just a choice. To me, it's just extra steps. We need something called the pKa to calculate. What were we given? We were given Ka. So 6.2 times 10 to the negative 8th. So the pKa is the negative log of that. And when we convert there, my screen reads 7.21. I think we have what we need to find pH. pH is going to be found by taking the pKa, we just solved, is 7.21, plus the log of the ratio of the millimoles of base over the millimoles of acid. Oh no, those aren't millis, those are actually true moles. Oops. Because that was a liter. There we go. Now I'm good. So here we had mole per liter, and finding the ratio of 0.0563 moles over the ratio of 0.1 mole. And when I hit that on my calculator, 7.21 plus the log of the ratio of 0.0563 over 0.1. That actually comes out negative, doesn't it? So the pH actually lowers, and you're going to have the final value of 6.96. And just remember to prove it to yourself, if you had done this with molarity units instead of just mole units, you would have 0.1126 over 0.2. I did a mole to mole ratio or molarity to molarity ratio, and you will indeed get the same number. What made this one different? Why did I pick it? Well, a couple of reasons. I noticed that they gave me grams, and sometimes when I'm starting off with a unit that I'm not familiar with, I'm going to think this is a tougher problem, but really it's not. They even did the hard work of giving us molar masses. So I did gram over molar mass to convert to a mole and just use Henderson-Hasselback from there. Once I had the moles of the acid and its conjugate base, I plugged it into the Henderson-Hasselback equation and pH came out directly. This one is my last one that I have. The molar solubility problem. So the last one I'll end with gives me a compound called barium phosphate. The only reason I picked it is it allows me to practice that coefficients. The barium ion itself, I get 3 of those coming out, and I can see that I get 2 of the phosphates, right? Those aqueous ions dissociate, and the quantity becomes there the coefficient. If the molar solubility is 8.89 times 10 to the negative 9th molar units, when it releases its barium ion, you're going to have 3 times that quantity. And when it releases the phosphate ion, you will have 2 times that quantity. And when you solve for the KSP, remember that the concentration of barium must be cubed and the concentration of phosphate must be squared. So plugging all of that into your calculator, the quantity of barium would be 3 times 8.89 times 10 to the negative 9th molar units cubed times the phosphate concentration, which is twice that of 8.89 times 10 to the negative 9th, and that actually ends up to be squared. So kind of just a final reminder of how to treat stoichiometry when solving for KSP. Barium phosphate, solving for its KSP in pure water, so no common ion, comes out to be a very tiny number, doesn't it? About 6.0 times 10 to the negative 39th on my calculator. Check it out though, be sure I'm correct. All right, I'm going to conclude our test review session. How long have I gone? Looks like about an hour and a half. So do this in small chunks. Thanks for sticking with me, and I wish you all the best on your test. Email with questions. Bye for now.